Attention, please. The show starts in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, go.
Good evening, everyone, and welcome to TECHSPHERE. We are delighted to welcome you for this session presented by IEEE Power and Energy Society and IEEE KIIT Student Branch. Today we are joined by our esteemed speaker, Dr. Poonam Tripathy, Associate Professor from the Department of Electrical Engineering at Rajdhani Engineering College, Bhubaneswar. Dr. Tripathy will be illuminating a critical topic of modern power system, that is power enhancement of phase-locked loops using a generalized integrator filters under adverse grid condition. Please join me in giving a warm welcome to Dr. Tripathy. Ma'am, you can start.
Thank you so much. Let me share my screen first. Is it visible to anyone?
Yes, ma'am.
Okay. Shall I start now?
Yes, ma'am.
Good evening, everyone. First of all, I would like to express my gratitude to the organizing committee members of TECHSPHERE for giving me an opportunity to deliver an expert tech talk on the topic performance enhancement of phase lock loops using generalized integrator filters under adverse grid condition. So I am Dr. Poonam Tripathy, working as an associate professor in the Department of Electrical Engineering from Rajdhani Engineering College, Bhubaneswar. The contents of my tech talk would present today, which are introduction, distributed power generation system, that is DPGS structure, phase lock loops, that is PLLs, control and design, summary of literature review, research gaps, research objectives, then SRA PLL, that is synchronously rotating reference frame PLL, then generalized integrator based PLLs, followed by simulation results discussion, conclusion, future work, and thereby references. Nowadays, in order to meet the increasing energy demand and to reduce the effect of greenhouse gas emissions, the renewable energy sources are integrated with the grid through the help of power electronic converters, which are basically known as inverters. So, a robust control of this grid interface converters is required in order to ensure that maximum amount of electrical power is being transferred from the renewable energy sources to the grid. So, basically, the synchronization systems like the phase lock loops are responsible for ensuring that the renewable energy sources injected voltage parameters, which are the voltage magnitude, phase angle, and frequency, must remain in phase with the utility grid's voltage parameters, that is voltage magnitude, frequency, and phase angle. So, among different types of PLL-based grid synchronization technique, the SRF PLL, that is the synchronously rotating reference frame PLL, is the most widely used one because of its simplicity and ease in implementation. But it has basically a drawback, that is, it operates well under only the ideal grid conditions, whereas it fails under in case of adverse grid condition. So the basic objective of my research work on this topic is basically to develop advanced phase lock loop techniques, which is basically done by the help of improving the performance of the existing SRF PLA by the use of some advanced filters, which are known as generalized integrator based filters, in such a way that the generalized integrator filter based SRF PLL will be capable of estimating the grid variables, which are basically the phase angle, magnitude, and the frequency accurately under any adverse grid condition by removing the effect of different types of adverse grid disturbances, leading to a robust synchronization. So the synchronization methods must account for the following features, which are The multiple disturbance rejection capability along with cancellation of noise disturbances, then adaptivity to frequency and phase angle, then robustness to voltage imbalances along with faster system dynamics with minimum convergence time, which basically refers to the minimum amount of settling time, along with structural simplicity, higher accuracy and least computational burden. So here this figure basically represents the structural presentation of a distributed power generation system structure. So see here initially the different types of renewable energy sources like the wind power, photovoltaic, fuel cells are connected with the main grid, that is our utility grid. And the utility grid is again connected with the local loads for the electrical power consumption obviously. So all the renewable energy sources are integrated with the utility grid through the help of power conversion unit, which may be a converter, which may be an inverter, depending upon their application. So the overall control system is basically classified into two types. One is the input side controller and the other one is the grid side controller. The functions of the input side controller is input power control, input side protection, maximum power point tracking, and generator speed control. Whereas the different types of control actions which are carried out through the help of grid side controller includes grid monitoring, grid synchronization, line impedance detection, DC link voltage control, active power control, and reactive power control. So basically the grid synchronization through the help of PLL ensures that the proper amount of active power flows from the renewable energy sources to the utility grid, whereas the reactive power control ensures the proper exchange of electrical power between the renewable energy sources and the main grid, that is our utility grid. So this slide represents the PLL or the phase lock loops control and design. So here you can see that this is a three-phase utility grid, and this side where the VDC represents the DC link voltage, which is used to determine any different types of renewable energy sources which are integrated with the three-phase grid. So basically, the renewable energy sources are integrated with the three-phase grid through the help of this power electronic-based converter. This is nothing but an inverter. So the inverter control is basically carried out through the help of PLL. So what does a PLL do? A PLL is basically used to achieve a robust synchronization by accurately extracting the features of the grid in terms of phase angle, voltage magnitude, as well as frequency. So once the PLL tracks the phase angle accurately with respect to any disturbed grid condition, any adverse grid conditions, like whenever the grid is affected with harmonics, subharmonics, interharmonics, frequency jump case, DC offset case, as well as voltage imbalances, sag, swell, any kind of grid disturbances. So it tracks the phase angle accurately in such a way that it is responsible for the production of the switching signals, which are ultimately given for the operation of the inverter. In this way, the overall synchronization of any renewable energy sources with the three-phase utility grid is maintained. So now coming to the PLL is basically a closed-loop nonlinear feedback control system which is used to synchronize its output signal with respect to its input signal in terms of phase angle. It basically has three components or parts, which are phase detector, PD, loop filter, LF, and voltage control oscillator, that is VCO. The phase detector is nothing but a comparator which is used to compare the input, that is the actual grid's phase angle, with respect to the output, that is the estimated phase angle determined by the PLL, in order to generate an error. Then the error is given as an input to the loop filter, which is basically a proportional integral controller, and it generates the output in terms of the frequency, that is the estimated grid frequency, which is then again given as an input to the voltage control oscillator, that is basically an integrator, which in return gives the output in terms of estimated phase angle. So overall, as among different types of PLL, the SRA PLL is the most widely used one. So in the next slide, I will be elaborating the functions of the classical or the conventional synchronously rotating reference frame PLL. Okay. Before jumping into that, I would like to mention about the different research gaps which are found from the extensive literature survey, which includes with the increasing penetration of the intermittent renewable energy sources with the utility grid, as well as due to the connection of different types of non-linear loads and the uses of the power electronic devices, many power quality issues arises. So the power quality issues adversely affect the performance of synchronization system. So to deal with this problem, designing of an efficient as well as robust synchronization system is very essential. So it must overcome the shortcomings like higher computational burden, implementation complexity, and with a very easy modeling and stability analysis, as well as inefficiency under larger frequency drifts, that which means the frequency jump case. So, an enhanced or a robust PLL method must be capable enough to accurately track the grid parameters like the voltage magnitude, phase angle, and frequency under any adverse grid condition with an enhanced disturbance rejection capability, minimum settling time, which ultimately leads to a faster system dynamics and a faster transient response in order to achieve a robust synchronization. So the research objectives are development of a simple, efficient, and robust generalized integrator-based frequency adaptive PLL, the synchronization system for a three-phase grid integrated distributed power generation converter. And the other one is an enhanced PLL designing with a very faster dynamic response along with efficient operation under normal and abnormal grid condition with higher filtering capability and simpler structure for the three-phase application. Okay, now coming to the uses as well as the idea regarding the conventional synchronously rotating reference frame PLL. So this is the PLL which is most widely used one because of the simplicity and easy implementation. Though it carries the drawbacks that it operates well only under the ideal grid case, and it is unable to track the grid parameters accurately under the adverse grid conditions. So obviously, to overcome its drawback, we need to develop some advanced as well as novel PLL method which have enhanced performance in comparison to the existing SRA PLL. So now coming to the SRA PLL, initially the three-phase voltage, that is VA, VB and VC are converted from the ABC, that is the natural reference frame or the three-phase reference frame, to the stationary reference frame or alpha beta reference frame, producing the output as V alpha and V beta through the help of Clark's transformation. Then the voltage parameters V alpha and V beta are converted from the alpha beta reference frame to the synchronously rotating reference frame, SRF, or the DQ reference frame through the help of Park's transformation. So here VD represents the direct component of the voltage, which is used to determine the voltage magnitude determined by V cap, and VQ represents the quadrature component of the voltage, which is used to determine the phase angle of the grid. And here the V cap and VQ must be equals to 1 per unit and 0 per unit in order to determine the efficient operation of a PLL. Once the phase angle or the quadrature voltage component is achieved, as we are going for the locking of the phase angle, so we are going for the locking of the VQ, that is the quadrature phase component of the voltage determining the phase angle. So the VQ is then given as an input to the proportional integral controller, that is the loop filter, and it is used to produce the output in terms of the difference in the grid frequency by comparing it with the actual grid frequency, that is omega n, which is 50 Hz or 100 pi radian per second. Then finally, the loop filter produces the output in terms of the estimated frequency, that is omega g cap, which is then given as an input to the voltage control oscillator, that is an integrator, which ultimately gives the output in terms of estimated phase angle. So these are the governing equation, and here Q is the phase shift operator, which is basically used to provide a phase shift of 90 degree for the orthogonal signal generation, that is V alpha and V beta. So for the orthogonal signal generations, now we are opting for the generalized integrator based filters, which leads to the enhancement of the performance of this classical SRA PLL. So a PLL must be capable enough to accurately extract the grid phase angle with respect to any operating grid condition. Now coming to the generalized integrator based PLL, any SRF PLL which utilizes a generalized integrator based filter for the performance improvement of the SRF PLL is known as generalized integrator based PLL. So the generalized integrators are nothing but proportional resonant controllers which are responsible for a higher filtering capability as well as the orthogonal or the quadrature signal generation, which means that the GI filters are basically implemented for producing the outputs which are known as the in-phase voltage component and the quadrature phase voltage component. Here, the orthogonal signal or the quadrature signal have a 90-degree phase shift with respect to the in-phase voltage signal, which I will be clarifying you. See. So here the figure 4 basically represents the structure of a generalized integrator based orthogonal signal generator. So we can see that for the input voltage V, by the use of two numbers of integrator, two outputs are generated. So orthogonal signals has been generated. One is V cap and one is QV dash. So V dash is the in-phase voltage component and QV dash is the quadrature phase voltage component or the orthogonal signal. Here RFS and QFS represents the transfer functions for the in-phase voltage component with respect to the input voltage V, and QFS represents the transfer function for the quadrature phase voltage component QV dash with respect to the input voltage V. The essence for deriving the transfer functions for the generalized integrator filters is that from the transfer functions, we can derive the Bode plot analysis from which we can determine that what is the disturbance filtering capability of each kind of generalized integrator based filter. So these are the developed or the advanced SRF PLLs. So first one is the dual second order generalized integrator based PLL. Here is two numbers of advanced generalized integrator filters named as SOGI. That is second order generalized integrator filters has been used. It is named as dual SOGI based PLL. So here the operation is as follows. Initially, the three-phase grid voltage, that is VA, VB, VC, are converted from the ABC or the natural reference frame to the alpha beta reference frame, producing the output V alpha and V beta through the help of Clark's transformation. Then the alpha beta reference frame, in the alpha beta reference frame, the output input voltages, that is V alpha and V beta, are responsible for the generation of the orthogonal signals, that is V alpha dash, QV alpha dash, V beta dash and QV beta dash through the help of two numbers of second order generalized integrator based filters. So after that, through the help of this generalized integrator based filters as well as the positive sequence calculation block, the fundamental frequency positive sequence components has been derived, which are V alpha plus and V beta plus. So the V alpha plus can be obtained by multiplying 0.5 with a differential value of the V alpha dash minus QV beta dash, and the fundamental frequency positive sequence component in the beta frame, that is V beta plus, can be obtained as 0.5 multiplied with QV alpha dash plus V beta dash. So once these fundamental frequency positive sequence components in the alpha beta reference frame are obtained using the instantaneous symmetrical calculation method in the PSC block, they are given as an input to the SRF PLL to estimate the grid phase angle accurately. So here you can see that the omega cap, that is the estimated grid frequency, is once again given as an input to the two numbers of SOGI based filters in order to make the overall PLL frequency adaptive in nature. So here comes the representation of the SOGI filter. Here, as in this generalized integrator based filter, two numbers of integrators has been used for the extraction of the orthogonal signal, that is in-phase voltage component V dash and the orthogonal signal QV dash with respect to the input voltage V. So it is known as SOGI filter, that is second order generalized integrator filter. So RFS and QFS represents the transfer functions of the in-phase and the quadrature phase voltage component with respect to the input voltage V. And here K represents the gain value of the SOGI filter. So from the SOGI filter, it was observed that from the board plot analysis, which was derived from the RFS and QFS, that the output V dash represent bandpass filtering nature, which means it inherently has the capacity to reject the effect of DC offset as well as harmonics. But the quadrature phase voltage component QV dash, from the board plot analysis of the QFS, it was found out that it exhibits low pass filtering nature, and hence it is only capable of rejecting the effect of harmonics, whereas it is not capable of eliminating the effect of DC offset. So now coming to the literature review point, though many advancement has been done for the elimination of the harmonic issue, power quality issue of the PLL system, till now zero attention has been given for the elimination of the DC offset based power quality issue. So basically this is the goal or the objective of my research work, is to eliminate both the DC offset as well as the harmonic power qualities issues in order to achieve a robust synchronization by accurately estimating the grid parameters through the help of a robust and novel PLL. So now here this represents one of the advanced PLL, that is known as D-TOGI PLL, which means dual third order generalized integrator based PLL. So as the SOGI based filter was having two numbers of integrators, ultimately by adding one more number of extra integrator, it was found out that it has led to enhanced filtering ability. So ultimately it led to higher disturbance rejection capability than that of the SOGI filter. So similarly, in this case, D-TOGI, two numbers of TOGI filters has been utilized for the extraction of the grid phase angle parameter for the achievement of the faster grid synchronization. Now coming to the block diagram of the TOGI filter, here you can see that as three numbers of integrators has been used for the orthogonal signal generation V dash and QV dash. With respect to the input voltage V, it is known as third order generalized integrator filter. Here two gains of the filter has been found out, which are K1 and K2, and from the board plot analysis, the optimized value of K1 and K2 was found out to be 1.1 and 2.82, whereas for the SOGI filter, it was found out to be 1.414. So it was observed from the board plot analysis, that is RFS and QFS of the TOGI filter, that the in-phase voltage component with respect to the input voltage exhibited bandpass filtering nature, and similarly, again, the board plot analysis of the transfer function QFS, which represented the transfer function of the QV dash with respect to the input voltage V, exhibited again low pass filtering nature. Though due to the uses of three numbers of integrator, the TOGI filter exhibited better or enhanced harmonic rejection capability than that of the SOGI based filter, but still it was not capable of eliminating the effect of the DC offset. So these are the transfer function equations of the TOGI based filter, and K1 and K2 represents the TOGI gain. So here comes the need for an advanced generalized integrator based filter, which must be capable of rejecting both the effect of DC offset as well as the harmonics whenever they are present in the input grid voltage in order to achieve a faster synchronization. So now there comes the development of a PLL, which is known as DMS-TOGI PLL, that is dual mixed second and third order generalized integrator based PLL. Here, as two numbers of mixed second and third order generalized integrator filters has been used, it is named as DMS-TOGI in order to achieve a robust synchronization of the renewable energy sources integrated at the grid by having a accurate as well as faster estimation of the grid phase angle with respect to any operating grid condition. So this structural diagram shows the representation of the mixed second and third order generalized integrator based filter. So here this part basically represents the previously showcased actual SOGI filter, as it had already two numbers of integrator. So to the existing SOGI filter, when an extra or an additional branch of integrator has been added, so it is named as second and third. So mixed second and third order generalized integrator filter. So the MS2G is responsible for the orthogonal signal generation, where the outputs are V dash and QV dash, that is the in phase and the quadrature phase voltage component with respect to the input voltage B. And from these, it can be studied that the transfer function R of S, that is the transfer function for V dash with respect to V, and Q of S, that is the transfer function for the QV dash with respect to V, both of them exhibited bandpass filtering nature, which confirmed their efficacy in eliminating the effect of both the harmonics as well as the DC offset, thereby achieving our objective. So these are the equations for the transfer functions of the MS2G filter, and these are the extraction of the fundamental frequency positive sequence component V alpha plus and V beta plus by the uses of the MS2G filters, which are then given as an input to the SRF PLL for the accurate phase angle extraction. So finally, coming to the simulation results, here a comparative result analysis of all the SOGI, TOGI and MS2G filter based PLLs has been done. So basically the performance analysis of DSOGI, DTOGI and DMS2G PLL has been done for 3 test cases, which are highly vital for any operating grid condition, which are the harmonics, then DC offset, and the third one is the frequency jump. So initially for this, the test case which has been considered is the 2-phase voltage sag with 5th and 7th harmonic. So from the simulation results, you can see that for a total time period of 0 to 0.5 seconds, in natural reference frame or the ABC reference frame, this shows the input voltage. So for the time period of 0 to 0.5 second, the disturbance consisting of 2-phase voltage sag with 5th and 7th harmonic has been introduced for a time period of from the time period of 0.1 to 0.4 second. Whereas the actual operating grid condition, that is 1 per unit with 50 Hz test case, has been maintained from the rest of the time period, that is 0 to 0.1 second, and after the grid disturbance case, that is 0.4 to 0.5 second. So the figure 12, 13 and 14 showcases the simulation responses of the DSOGI, DTOGI and DMS2G PLL in ABC or the natural reference frame under the 2-phase voltage sag with harmonics test case. So it can be seen that all the PLLs are capable of eliminating the effect of harmonics effectively by accurately estimating the producing the 3-phase grid voltage in the ABC reference frame. Now, these simulation responses showcases the PLL responses in the DQ reference frame. As previously I said that the VD represents the magnitude of the voltage which must be equal to 1 per unit, and the quadrature phase voltage component VQ that represents the phase angle must be equals to 0 per unit in order to determine the accurate operation of any PLL. So from the simulation responses of all the PLLs in the DQ reference frame, it can be seen that for the disturbance time period from 0.1 to 0.4 second, all the PLLs are capable of accurately estimating the voltage magnitude as well as the voltage phase angle. So they can accurately estimate the grid parameters under the 2-phase voltage with 5th and 7th harmonic test condition. Now here, this simulation responses show the frequency comparison of all the estimated frequency by each PLL with respect to the actual operating grid frequency, that is 50 Hz. So it can be seen that during the disturbance condition, all the 3 PLLs are capable of accurately estimating the grid frequency, that is 50 Hz with respect to the reference 50 Hz, that is the normal grid's frequency. So these simulation responses show the amount of TST content in the output signals by each PLL. So the total amount of harmonic content in the output signal is basically analyzed through the help of FFT analysis, which is the first Fourier transform, which determines that all of them are having a TST content which is well within the IEEE standard, that is less than equal to 5%. So here, the SOGI exhibits a TST content of 3.24%, TOGI filter-based PLL 1.34% and the MS TOGI filter-based PLL showcased 3.96%. So all of them are efficiently capable of estimating the grid parameters by rejecting the effect of the two-phase voltage sags with harmonics. Now here the second test case has been considered, that is the presence of DC offset, which is the most burning issue in the grids now, because till now almost nil attention has been given for the curtailment of this DC offset issue, power quality issue, for achieving a robust synchronization in the grid integrated with the distributed power generation system. So these simulation responses basically show their performance, and here the figure 24 represents the input signal along with a DC offset disturbance condition from the time period of 0.1 to 0.4 in natural or the ABC reference frame. And these simulation responses showcase that here the SOGI filter based and the TOGI filter based DSOGI and DTOGI PLL are not capable of accurately extracting the voltage magnitude in the ABC reference frame. You can see the outputs as well. This was the input signal carrying the distortion, and here you can also see the output signals which has been extracted by the DSOGI and the DTOGI PLL. They are still consisting of the DC offset disturbances. But here comes the advantage of the DMS TOGI PLL, and it is accurately and precisely estimating the grid voltage magnitude by eliminating the effect of the DC offset whenever it is present in the grid. So here, similarly, this was the simulation responses of all the three PLLs in the DQ reference frame, that is the synchronously rotating reference frame. So it can be seen that the voltage magnitude representing the VD, that is 1 per unit, and the voltage phase angle representing the VQ, which must be equal to 0 per unit, has only been achieved in case of the DMS TOGI PLL. So this MS TOGI filter based DMS TOGI PLL is only capable of eliminating the effect of DC offset by accurately estimating the grid parameter, whereas these two PLLs, that is the DSOGI and DTOGI PLL, fail miserably under the DC offset test condition. Now coming to the simulation responses showing the frequency comparison of all the three PLLs with respect to the normal operating frequency, that is 50 Hz. Again, it can be seen that these two PLLs, SOGI and TOGI filter based PLLs, are not capable of extracting the grid frequency in case of the DC offset test condition, whereas this PLL is efficiently and effectively eliminating the effect and is accurately estimating the grid frequency with a very minimum settling time and with no oscillatory system, means having a steady state response. So these are the simulations responses. Though we do not require any TSD analysis in order to determine the performance evaluation considering the DC offset test case, still it has been carried out, and it was observed that all of them are having a TSD content well within the IEEE standard limit, that is less than equal to 5%. Now this is the third case, that is the frequency jump, which is one of the another most vital and most recurring test case in any grid operating condition whenever the grids are interconnected with renewable energy sources. So here this was the first figure. The figure 37 represents the input grid voltage, where a frequency jump test case has been provided from a time period of 0.5 to 1.5 second, and these are the simulation responses of all the PLLs in the ABC or the natural reference frame. So it can be seen that all the PLLs are capable of estimating the grid parameters accurately in the ABC reference frame. You can see the output signals. This was the distorted input signal consisting of the frequency jump case from the 50 to 50 Hertz, 55 Hertz. See, basically the frequency change must range between a limit of plus or minus 2%, but still I have led to a critical issue, that is a very higher level of frequency jump case. So I have taken a plus 5 Hertz of frequency change. Still all the PLLs are capable of eliminating the effect of the frequency jump test case, and they are capable of estimating the grid parameters accurately, leading to a robust synchronization. So again, these are the DQ frame responses of all the PLLs. It can be seen that all the PLLs are capable of estimating the voltage magnitude as well as phase angle accurately. Similarly, these simulation responses once again show the frequency comparison of all the three PLLs responses with respect to the actual grid operating frequency, that is 50 Hz. And see, here the normal grid operating condition was 50 Hz, and for the time period of 0.1 to 2 seconds, we had provided a frequency jump case. So the frequency jump is from 50 to 55 Hz, and all the three PLLs are capable of estimating the frequency jump case accurately. So see, here they are also tracking 50 whenever the grid frequency is 50. Similarly, whenever there is a frequency jump of 55, again all the three PLLs are also accurately tracking the frequency jump with 55 Hz case. So definitely all the PLLs are capable of accurately estimating the grid parameters efficiently, leading to a robust synchronization. So these are once again the TSD analysis showing the that all of them are well within the IEEE standard limit, that is less than equal to 5%, showing their efficacy and advancements. Now, finally, coming to the tabular comparison, the table 1 represents the comparative performance analysis of the generalized integrator pre-filter based PLLs under different test conditions like two-phase voltage sag with 5th and 7th harmonic, DC offset test case, and frequency jump case in terms of different features like settling time, which basically showcases the convergence time or the system dynamics, and the TSD content in the output signals. So from the tabular comparison, it can be seen that though DSOGI and DTOGI PLL are capable of eliminating the effect of the sag with harmonics as well as the frequency jump case, but they fail miserably under the DC offset test condition. Whereas it can be confirmed that the DMS-TOGI PLL has a superior performance in comparison to the SOGI and the TOGI filter based PLL, showcasing an advanced filter disturbance rejection capability with a faster system dynamics, minimum settling time, minimum TSD content, leading it to be a advanced as well as robust grid synchronization technique, which must be suitable for the integration of the renewable energy sources with the utility grid. So finally, coming into the conclusion part, a comparative study of different generalized integrator based PLLs has been studied in order to overcome the limitations of the classical or the conventional SRF PLL, as the SRF PLL was only able to operate well under the ideal grid condition, but it failed miserably under the different adverse grid conditions. So there comes the necessity for the development of advanced SRF PLL, which led to the development of a SOGI filter based PLL, which once again failed miserably under the DC offset test case. The DC offset test condition is one of the major power quality issue which has been given nil attention till now in our literature. So the objective was to develop advanced and robust grid synchronization technique which must be capable enough to eliminate the impact of the varieties of the grid disturbance test condition in order to achieve a robust synchronization with minimum settling time, minimum TSD content, and faster system dynamics, along with least system complexity and ease in implementation. So finally, it was found out that the developed TOGI filter-based PLL, though exhibited better harmonic rejection capability than that of the SOGI filter-based PLL, but it was unable to eliminate the effect of DC offset, whereas the MS-TOGI filter-based PLL was capable of achieving a robust grid synchronization along with multiple disturbance rejection capability, minimum settling time, minimum TSD content, which made it a superior as well as robust and novel GI filter-based PLL technique, which can be implemented for the integration of the distributed power generation systems with the existing utility grid. So finally, coming to the future scope. In future scope, I am basically looking forward to develop some hybrid PLLs which can lead to curtailment of further more disturbances to which till now no attention has been given, like subharmonics, interharmonics. considering also the minimum number of uses of integrators, which would lead to the least amount of complexity, and but leading to a robust grid synchronization technique. Then the PLL, which is having three numbers of components, that is the phase detector, loop filter, as well as the voltage controller. Each part can also be modified in order to develop a robust PLL. So that is also one of the future scope. Apart from that, different optimization techniques can be implemented to find the optimum value of the filter gains, which would also lead to a robust grid synchronization technique. So these are my upcoming future scope on which I am basically focusing to work on. So these are some of the major references which I had referred for my research work. Thank you so much.
Thank you, Dr. Tripathi, for that highly informative and essential presentation. We deeply appreciate you taking your time to share your expertise on performance enhancement of phase locked loops and GI filters with the TECHSPHERE audience. Now, I would like to respectfully invite Professor Chinmay Kumar Panigra, SMI EEE, Director, School of Electrical Engineering and Co-branded Programs, KEEP DU, Vice Chair of IEEE Bhubaneswar section, to kindly share a few words. Sir.
My voice is audible.
Good evening, sir.
Dr. Poonam, I am listening. The way
Yes,
you are
sir.
presenting, you are saying and delivering dialogue. I think Dr. Banishri is also there in this.
Yes, sir. Ma'am is also
Yes, sir.
there.
Yes, sir.
Good
Ah,
evening,
Good
that's
ma'am.
evening, sir. Good
ah,
evening, sir.
very good.
Good
Dr.
evening, madam.
Poonam,
Good evening.
your style, your presentation skill, I appreciate. Niharika is the right person, our anchor. She has chosen the right topic regarding PLL, phase locked loops under generalized and advanced grid conditions. Is it right, Dr. Poonam?
Yes, sir.
Ah, so what I
Thank you so much, sir.
understand, what I understand regarding this grid voltage distortion, number one is the grid voltage. You are just saying about the grid voltage distortion. What are the challenges that you have elaborated very nicely, harmonic and interharmonics? And second point, you have highlighted voltage imbalance, negative sequence components. And number three, again, some challenges as for the scope you have mentioned very rightly, frequency deviation and fast frequency ramps, which is the high risk scenario for the microgrids, renewable dominated grids, particularly PV and islanding transitions. And another is very important is challenges as the people who are in the online mode. They should understand what is the low circuits ratio SCR for weak grid conditions. Weak grid have high impedance causing voltage drops and oscillatory behavior. And we have to understand the challenges grid disturbances directly affect the PLL input. Coupling between PLL dynamics and converter current controller can use also instability, voltage instability. And number five, I want to highlight just adding some values of your talk, voltage, sex, swells, and fault conditions. Issues is grid fault, drastically distort voltage, amplitude, and phase. Whenever we are seeing challenges, PLL can misinterpret abrupt voltage changes as phase shifts. Severe sex can cause PLL unlocking. I request Dr. Poonam, you to rethink about these are the challenges you have to make the solution how to solve the fault right through FRT.
Yes,
Fault
sir.
right through requirement stress, PLL robustness. And number six is noise and measurement errors. That is a very, very important because whenever we'll go to the real-time system, Dr. Banich will agree to me, issues like sensors, ADC, quantization, and depend switching noise effect, measured voltage challenges, PLL output voltage, phase currents, ripple, reduced accuracy in high frequency applications. Noise may lead the false synchronization, which is a very important constraint in the power system. And again, another point also I want to highlight who are sitting, research scholars and all the people. Non-idealities, filtering and delay effects, PLL, use filters, challenges is PLL, filter decays, degrade, dynamic response. Adaptive filters may become unstable during transients. Then coupling effects in converter control loops. Dr. Poonam, PLL interacts with the current voltage control. This is the issue. As
Yes.
you have told very rightly in the conclusion, the challenges again, whenever we are seeing coupling effects in converter control loops at the time, challenges is incorrect PLL turning. Niharika, try to understand these are the issues you have to, Robindu. You are now in second year and take you should. It is a very good topic. How the real time incorrect PLL turning can destabilize the whole converter. Poorly turned and PLL creates resonances with the LCL filters. Then very important is a black start and reconnection challenges during issue is during grid restoration and reconnection after islandings. Grid signals are irregular. Challenges. What are the challenges? Again, we have to all the research scholars. It is a very research topic. Initial conditions unpredictable that we know PLL lock time greatly increases, and these are the just in my own way I'm giving some suggestion. Who are the research scholars and also people who are listening to me, you have to understand this is the very important topic in power system, that is the challenges of PLL under generalized and advanced grid condition. Just I'm concluding, PLL means phase locked loops are essential for synchronizing grid connected converters with the utility grid. However, when the grid deviates from ideal sinusoidal balanced conditions, PLLs face significant difficulties. So this is from my side. Again, these challenges largely determine the stability, accuracy, and dynamic performance issues. This is Niharika. I'm happy with the Dr. Poonam, the way she has made the dialogue, and each slide is very, very effective and then also informative. I'm just giving in my own way how another next 1 year or 2 year you take how this type of challenges whenever we are saying PLL. So how the adverse grid conditions, because only the constant is your wind and PV. Whenever grid is disturbing these two people, so we have to be very careful. So with this, I appreciate Dr. Poonam, your wisdom, your knowledge, and also the way you are delivering. That is the great attitude of a good teacher. I'm happy to see that you are the associate professor also. That's
Thank you
my
so much.
blessings is to you. So, so you think the objective why we are making Saturday only to understand networking, we understand the project, we understand the patent, because the real research starts after getting the PhD degree. Today, Dr. Banish will also agree to me how we'll make more people connected through this so that our bonding, our talent, our wisdom, our knowledge can be well shared in a positive vibes. Thank you, Dr. Poonam, Dr. Banishri, and also Niharika. Over to Niharika, please.
Thank you, sir.
Thank you so much, sir.
Whatever challenges I told Dr. Poonam, is it clear to you?
Yes, sir. Very rightly said.
Thank you, thank you. Dr. Banishri, is it the things we have to solve?
Yes, sir, definitely.
Good,
Well,
good,
thank
good.
you.
Okay. Niharika,
Thank
over to
you.
Niharika.
Thank you so much, sir, for your inspiring and encouraging words. Now, I would like to invite Banisri ma'am to talk few words.
Hello, am I audible?
Yes, ma'am.
Thank you, Niharika. Thank you so much, Manigri sir, for appreciating the presentation of Poonam. So, lot many challenges in the area of grid synchronization, as she has correctly mentioned, and lot many work has to be done. I know her for the last 5 to 6 years. She's working, and she's a very dedicated girl. And I know she will enhance her work and extend her work in future also. Lot many challenges. You can work, Poonam, on the subharmonics area.
Yes,
Also interharmonics with a lot many advanced PLL that you can design, that you have already said the hybrid PLL structures, you can go for that.
yes, ma'am.
And you can address the issues of subharmonics and interharmonics, which is basically much more importance in the wind turbine system, grid integrated wind systems. So you keep that in mind and just do your research, further research. So I can see a lot of confidence, Poonam. Thank you so much. So you are growing a
Thank
lot.
you.
Yes,
Yes, yes. A lot of
congratulations.
confidence because of you.
Yes. Thank you so much, sir. Thank you so much. So
Thank
you
you.
please grow, and I know you will do your best. I know you have the potential. So take it in the right spirit and go in the positive direction. All the
Yes.
best to you.
Thank
All
you,
the
ma'am.
best.
Thank you
Poonam.
so much. Thank
All
you,
the
sir.
best. Okay. Thank you.
Thank you, everyone.
Thank you.
Thank you, Banishri ma'am, for your encouraging words. Now, I would like to, on the behalf of IEEE PES and IEEE KIIT student branch, we extend our sincere gratitude to Dr. Poonam Tripathy, Professor Chinmay Panigra, and Banishri ma'am for gracing this event with their presence and guidance. And a heartfelt thank you to all the participants for joining us today. We look forward for seeing you at our next event. Now, I would like to tell sir, ma'am to open their video once for the picture, and we will show your certificates. We will show the certificates digitally.
So congratulations, Dr. Poonam. Very good certificate our people are doing. Very nice.
Thank you so much, sir. Sir, namaskar.
Namaskar, namaskar.
Thank you, everyone, and have a wonderful good night.
Good night. Thank you,
Good
Niharika.
night.
Very nice.
Bye-bye.
Thank you, sir.
Thank you. Thank you, sir.
So
Thank
thank
you,
you.
everyone.
Bye, Poonam. Bye. Have a nice
Ma'am,
day.
namaskar again.
Bye.